Hello everyone, here we'll be discussing vector fields, and the first thing I want to say is that a vector field on Rn is a function f, capital F, so it's a vector function, capital F, that assigns each point in Rn, well in a subset of Rn that is, so let's call it x1, x2, all the way to xn, to just f of that point. Now this is a very general statement, but I wrote it as like, I wrote it general like this to avoid writing two scenarios. But there are two scenarios that we'll kind of mainly be focusing on, which are R2 and R3. So let me just say specifically, when n is equal to 2, our point looks like x comma y, and usually we're taking it in a subset D that's a subset of R2, if that makes sense. So when n is equal to 2, we have this because it's R2 instead of Rn, and f will just be of x comma y. So I know here I wrote it in this kind of way because n in general could be whatever number, and if it's beyond 3, then we'll have to go beyond z and x, y, z, so to speak. So we label with subscripts of x in that case, but in specific when it's R2, we just use x, y like usual. And you can kind of imagine what it would be for n equals 3. That would be the point x comma y comma z, and usually we call the subset that this point would be in R3e, and this should remind us of what we've been seeing for double and triple integrals. Double integrals, we take the integral over the region D. Triple integrals, we take the region over, well, we take the triple integral over the region E. That makes sense? And here, the vector function, or vector field, will be f of that point x, y, z. So really all that is just essentially a vector function, but just in a very specific notion, a very specific notion of that. And usually we use the letters p, q, and r as the function of each component. So for example, f of x comma y comma z is going to be equal to q of, well, I guess it would be p of, so it would be p of x comma y comma z I plus q x comma y comma z j, so these are the components, and then r of x comma y comma z of k, or times the vector k. So recall that for a vector function, that's usually of some letter t, and then each component is evaluated at that. So this is a little different because each of our components here are now going to be, well, functions of multiple variables. So that's really the key difference here, so I hope we kind of understand that. So now we'll take a look at an example of a particular vector field. Okay, so actually I only want to take a look at this one example. It's kind of a simple one, but it'll at least give us a really nice idea, visually anyways, what vector fields really do for us. So now let's take a look at this example here. So let's define the vector field f over R2, or on R2, by f of xy being equal to the vector negative yx. So now let us describe the vector field f by sketching some of the vectors f of x comma y. Now to do that, I think the best thing to do really is to get an idea by considering the table that sends each point x comma y to that vector field f of x comma y. Now the points I really want to consider are on a particular, well, I guess, particular points for xy values, or on the xy plane I should say. So let's do this. Let's draw an xy plane. And it would be nice to consider, let's say, a 3x3 grid, just to get an idea. So let's just go 3 in each direction. We could go further, but I'm just going to go 3. And you'll see it should be enough to get an idea as far as what the visualization is. So just to get an idea, let's consider something like, how about 1, 0. So if you apply 1, 0 into this, then now notice that the swap and the y gets negated. So we get the vector 0, 1. So what this tells me is that for the point 1, 0, which is this point here, we get this vector 0, 1, which has an x component of 0 but a y component of 1. So it represents this vertical vector of magnitude 1. Okay? What about, let's say, I don't know, 0, 1 instead? So this again swaps them but negates the y value according to our assignment there, or I guess our function if you will. So we swap them and negate the y value, we get this. So now 0, 1 is this point right here, x equals 0, y equals 1. And negative 1, 0 is the vector who has no y component, but it has a negative 1 x component, meaning its magnitude is 1. So we get something like this. Awesome. And you might imagine that if you were to try negative 1, 0, again, if you kind of swap these and negate the y, it doesn't really matter because it's 0, so we end up getting 0, negative 1. Meaning at negative 1, 0, we get an arrow facing down. And as you might imagine, at 0, negative 1, we get negative 1, 0, like that. Or I guess it's positive 1, 0. So let me just draw that. So that's 0, negative 1, then the point will go to the vector positive 1, 0. There we go. So that makes sense, I think. We're okay there. But now what happens for other points? Like, let's say, for instance, what about the point 2, 2? Or negative 2, 2? Or negative 2, negative 2, or 2, negative 2? Something like that. Well, it's not too hard to see what happens, but I'll just draw one particular, and then from there I'll kind of show you what they look like, and kind of just go based on the pattern. But yeah, if you consider the point 2, 2, for instance, the vector that it goes to according to that assignment is negative 2, 2 like this. So for the point 2, 2, we're going to go right to, or left to, I guess you should say, in the negative direction, and then up to. So what we end up getting is this vector that goes over to this way and up to this way from this point. Now this should make sense because remember that these vectors, like this vector here, in the standard position is really from the origin to the point negative 2, 2. But we're floating it around in such a way that we want its tail end to be on this point that it's assigned to. So with that being said, if we were to take a look at the point negative 2, 2, then if we swap those and negate y according again to that assignment, we get negative 2, negative 2, meaning that this arrow is going to go down 2 and to the left 2. So down 2 and to the left 2 will look something like this. So now at this point, I think what I'm going to do is just, again, generalize it. So this point here will go like this point here will go like this. And if you wanted to go to 3, 3 to see what that looks like, you'll get a pretty good idea of what's going on here. And what actually ends up happening is that, and we can actually check this on our own if we like, all of these vectors are actually points that are, well, each vector I should say, is a vector that is perpendicular to the radius of a circle. In other words, it's tangent to a circle of that radius. So these points would be on a circle as well. Now the radius of that circle isn't quite what you'd imagine it to be, just because they're kind of like at these diagonal points, but still it goes to show that it's like, and I'm only showing a few of these, but if we were to do a few others, then we kind of see this kind of spiral image. But not only do they spiral in a counterclockwise fashion, but again, the arrows have larger magnitudes depending, well, basically the further out you go. So that I think is a nice visualization. That's really all I'm going to say there. I think that suffices, so that's enough really. So now what I'm going to do is define something a little different based on vector fields, and I think that'll actually be it for this video. Right, so for this last idea here, we want to say that the gradient of a function f, referred to as del f, so this symbol is del. I know I've said in the past that del is the partial derivative symbol, but that's just what I've heard people say. The official naming of, the official symbol called del is this. Partial derivative symbol is just called partial, as it turns out, officially. But I've heard people call it del. It doesn't matter. Now, this gradient, del f, is the vector whose components are the corresponding partial derivatives of the function f. In other words, del of f xy, the gradient of f of xy, is fx, so the derivative with respect to x, partial with respect to x, I, plus partial with respect to a y, j. So notice this in component form is really fx comma fy. Or with partial notation, this is partial f over partial x, comma partial f over partial y, like that. And I wrote something similar for f in 3 variables, x, y, z, but I wrote it in component form with a partial notation, just to show different variations of the notation. Okay. Now, Since each partial derivative is a function of the variables x, y, and possibly z, in the case of 3 variable functions, then that means that, so this should be then, del f, the gradient, is actually a vector field and is referred to as a gradient vector field. So if I ever ask you to find a gradient vector field, all I'm asking you really to do is to find this gradient function, or gradient of the function. So for instance here, I want you to find the gradient vector field of this function of 2 variables, x squared y minus y cubed. All we have to do is take the partial derivatives and write those as components of a vector. So that's called del f, technically of x comma y, and that is the vector whose x component is the derivative with respect to x, partial derivative with respect to x. Notice the derivative of x squared is 2x, y is a constant, so it comes down to 3 by constant multiple rule, sorry. Y cubed is a constant in respect to x, its derivative is 0 then. Now for the y component, we take the partial derivative of f with respect to y now. This is going to be a constant times y, whose derivative is just x squared, just the constant itself. Derivative of y cubed with respect to y is negative 3y squared, and that's it. So I'll box this. And if you want to actually plot this to get a visualization like I showed with the previous example, you can certainly do that, but I'm not going to. In fact, this is a pretty short discussion on vector fields. That's all I want to say actually. But we'll see a lot of this and more. In fact, one last thing I kind of want to bring up is this idea of what is called a conservative vector field. Now we won't actually see that for a while, but I'll just say it out loud here just so it's kind of embedded in your mind a little bit. A vector field is conservative if it is a gradient vector field of some function, which I know sounds funny. As it turns out, not every vector field is conservative, but there are some that are, and we'll actually have a theorem that will that'll have something to do with that later on. But I just want to kind of say that out loud without writing it down. But I'll write it down to remind us in the later videos. But right, with that being said, I hope you enjoyed this video. That's really all I want to say as far as vector fields are concerned. And I'll see you in the next videos. Thanks for watching, and like always, I'll see you then.